Astronomy research has done some amazing stuff. Over the past century or so, we've discovered how stars form and where the solar system came from. We've discovered thousands of galaxies full of other stars and planets throughout our universe. We know the universe had a beginning, and we have evidence of the afterglow of the Big Bang. There's a lot to be proud of, a lot of real successes of science. But I'll be the first to admit that science doesn't know everything. If science knew everything, it'd stop. And astronomy is still going strong, because there are some pretty massive things we don't know yet about the universe. So as my first science video of 2025, I thought I'd go through my entirely unordered and unranked top 5 unsolved questions in astrophysics today. These are, of course, not the only unanswered questions in astrophysics, but they're probably some of the biggest ones that when we do answer them, we'll learn a whole load of new stuff about the universe. Essentially, I've gone with the ones where I think that there's the most scope for new groundbreaking discoveries. But before we go any further, make sure to subscribe and hit the bell icon so you don't miss future videos. Unanswered question number 1. Where are all the Earth-like planets? With a follow-up, do they support life? Currently, humanity is aware of one planet in the universe that is capable of supporting life. It's Earth. That's it. Despite searches for life across the solar system and scanning the skies for Earth-like planets, Earth is the only place we know of that has ever supported life. But our galaxy is home to about 1 billion stars. Surely Earth isn't some kind of solitary unicorn in the cosmos. The more we've learned, the more average our solar system appears. The Sun is a fairly average star. The solar system is in a fairly average bit of the galaxy, and the Milky Way galaxy is a fairly average spiral galaxy. Chances are that there are other Earth-like planets out there. So that brings us back to our question. Where are they? Most of the exoplanets we've found, that's planets around other stars, they're not like Earth. They tend to be more massive and orbit much closer to their star. There are, of course, 2 possible explanations for this. Either Earth is indeed weird, and most planets are these more massive, hotter variety, or we're just not finding the Earth-like planets. Good news! We're probably just not finding them. Not so great news, it's because all of our methods are rather biased. We have 4 main methods for finding exoplanets, and none of them favour finding Earth-like planets first. The most successful method we have is known as the transit method. This involves watching stars, looking for dips in their starlight as an exoplanet passes in front of them, or transits. This method is by far the simplest method we have. We're just watching for changes in brightness. However, this simple method is biased in 2 ways. The first is very simple. A bigger planet is going to block more light. It's easier to detect a bigger change in the brightness from a star. The second bias comes from the intricacies of confirming an exoplanet transit. One isn't enough. Any number of things can cause a star to dim. It could be sunspots, it could be some interstellar dust passing in front of it. We need multiple detections of the transit to confirm that it is indeed an exoplanet. So, along with the bias towards the larger planets, we're also going to be biased towards planets that orbit their stars more frequently. We'll confirm a planet that orbits once a week much faster than one that orbits its star once per Earth year. To confirm the detection of an Earth-like planet orbiting a Sun-like star, we'd need to have a detector sensitive enough to detect the dip in the star's brightness caused by that transit, and we'd also need to wait multiple years to get enough transit observations to confirm it. So, not great. Our other methods are also biased away from Earth-like planets. The radial velocity method has also been very successful at detecting exoplanets by looking for slight wobbles in the wavelengths of starlight caused by the motion of an exoplanet. This is because of a common misconception that planets orbit otherwise stationary stars. They don't. In reality, gravity pulls on the planet, but also on the star. This means that as the planet orbits the star moves a little. This movement causes small Doppler shifts in the light, making it appear slightly redder then slightly bluer than it otherwise would if the star was stationary. Since this depends on gravity, larger exoplanets are going to lead to bigger shifts in the wavelengths of these stars. So again, we're biased towards more massive exoplanets. Direct imaging. Literally taking a picture of the planet is technically difficult. You've got to block out the starlight. And it's, again, biased towards more massive planets because they will reflect more starlight. And then the final method, microlensing, the momentary brightening of background sources because of the gravity of a planet, also depends on gravity, so it will also be biased to more massive planets. What all of this means is that these so-called hot Jupiters, these massive planets orbiting close to their stars, these are essentially the low-hanging fruit of the exoplanet population. They're the easiest to find, so it makes sense we found them first. Detecting Earth-like exoplanets is going to be a little bit harder, but far from impossible. We currently think that around 30% of Sun-like stars in our galaxy will host an Earth-mass planet, a planet the same mass as Earth. This doesn't mean they'll all be habitable, but they will be the right size. Our best bet for finding these exoplanets may well be NASA's upcoming Nancy Grace Roman Space Telescope, due to launch by May 2027. It will use the microlensing method to hunt for Earth-mass exoplanets, magnifying the brightness of background stars and galaxies. This will hopefully fill out a bit more of the exoplanet census for us. But even if we do find these Earth-mass exoplanets, we won't know if they're actually Earth-like. We actually know very little about most exoplanets, beyond where they are and how massive they are. The James Webb Space Telescope has started to help with this. It's been taking spectra of the light that passes through exoplanet atmospheres during a transit, trying to figure out what they're made of based on the amount of light that's removed by different elements. But for these Earth-mass exoplanets, they won't transit very often, so transit spectroscopy probably won't work. We'll have to wait for the Habitable Worlds Observatory, currently planned for the 2040s, to take direct images of these exoplanets and figure out what their atmospheres are made of. So the question of Earth-like exoplanets probably isn't going to be solved anytime soon, but I won't be surprised if we find one within my lifetime. Our next unsolved question takes us very much into the unknown. What are dark matter and dark energy? Straight off the bat, they are not the same thing. So let's start with dark matter. Under our best model of the universe, known as lambda CDM, about 25% of our universe is made up of this something we call dark matter. The CDM in lambda CDM actually stands for cold dark matter. We think dark matter is a thing because we have an absolute deluge of data that says it does. But the story, it starts with Vera Rubin, an astronomer at the Carnegie Institution in the late 60s and early 70s, who measured the rotation curves of galaxies, measuring how fast stars and gas in galaxies was rotating around its galactic centre, and how that speed changes with the distance from the centre of the galaxy. What everyone expected looking at Newton and Einstein's laws of gravity was that the outsides of galaxies would rotate slower than the inner regions, much like how Mercury orbits the Sun faster than Pluto. Vera Rubin did not find this. She found the rotation curves of galaxies were flat. Outer regions were rotating at the same speed that inner regions were, and in a paper from 1980, she presented her results and determined that more than 50% of the mass in galaxies would actually have to be in a dark halo around the galaxy to explain these rotation curves. Fast forward a few decades, and this so-called dark matter is a core part of our best model of the universe. It explains the masses we measure from observations of galaxies and galaxy clusters, and when we include it in simulations, it gives us a universe that looks like our own. The only problem is, we have no idea what it is. Okay, there are some ideas. Some people think that the standard model of particle physics is incomplete, that dark matter is a particle we need to detect. Particle physicists at CERN and other facilities are building experiments to look for energy missing from particle collisions that could be a sign of the production of dark matter particles being undetected and leaching away energy from the reaction. Some astronomers think that perhaps dark matter just doesn't exist and that there's something wrong with general relativity. That's Einstein's theory of gravity. There are various other alternative theories, all of which have their own issues, but it's an idea. The last idea is that dark matter is just something really hard to detect, like primordial black holes, hypothetical small black holes produced in the early universe. If this one is correct, that will open a whole new kettle of fish trying to explain them, but we'd have to find them first. In attempts to help us figure out what exactly dark matter actually is, the European Space Agency's Euclid Space Telescope is currently observing gravitational lensing by galaxy clusters, a big version of the microlensing I mentioned for exoplanets earlier on, and attempting to use that to build a map of dark matter across space and time. The Vera-Rubin Observatory will also do this from the ground when it comes online later this year. As for dark energy, this is another big unknown. Some mysterious force that makes up about 70% of the universe and is powering its expansion. Now we know that the universe is expanding. It is literally getting bigger, because we can see distant galaxies moving away from us by taking spectra of their light, splitting it up into its various wavelengths, and we see that that light is redshifted. It appears longer than it would if the galaxies weren't moving. What's really trippy is that the galaxies that are further away from us are actually moving away faster than those closer to us. Surveying the sky, we know that the expansion of the universe is getting faster. But logically, gravity should be pulling everything together, so something is moving things apart and making space literally bigger. That something is what we call dark energy. But we actually really have no idea what it is. We're pretty sure it's not directly related to dark matter, not how normal mass and energy are related by E equals mc squared, but that's about it. Fortunately, all the stuff that we're doing to try and figure out what dark matter is will also help here. The Euclid Space Telescope is measuring the shape and redshifts of galaxies, which will help us improve our estimate for the expansion rate of the universe. And when the Roman Space Telescope launches, it'll probe the large-scale structure of the universe and measure the effects of dark energy, whatever that is. Speaking of measuring the expansion rate of the universe, this is a cornerstone of our best model of the universe, lambda CDM. But what if lambda CDM is just wrong? This third unanswered question is a bit concerning for cosmologists because, well, lambda CDM is great at a lot of things. We have an absolute deluge of data supporting it, and it explains so much of what we see in the universe. No one really wants us to have to start over. However, for over a decade now, there's been this crisis in cosmology, which is also known as the Hubble tension. This crisis has arisen because our two best methods for measuring the expansion rate of the universe just don't agree with each other anymore. These two methods are quite different. One measures the expansion rate of the universe based on the local universe, using objects known as Cepheid variable stars. These are stars which pulsate, and there's a really well-defined relation between their brightness and the frequency of that pulsation. The other method is based on the cosmic microwave background, the afterglow of the Big Bang that's been redshifted over the last 13.8 billion years to now sit in the microwave part of the electromagnetic spectrum. Up to about 2013, things were alright. The uncertainties in the expansion rate from both methods, this value known as the Hubble constant, were large enough that both methods agreed with each other within their uncertainties. As our measurements have got better, they've started to diverge, so that now, and for the past few years, they have completely disagreed. So one of two things must be happening here. Either there's something wrong with the measurements of the expansion rate of the universe, or there's something wrong with our best model of the universe. Either way, there's something new to learn, which is great for astronomers. But how are we going to solve this crisis in cosmology? Good question. Here are some of the ideas. The most obvious thing is that there's something wrong with our measurements of the expansion rate of the universe. We thought the launch of the James Webb Space Telescope might resolve this, but as yet, no luck. But there are more telescopes now, or soon to be observing, including the Euclid Space Telescope, the Roman Space Telescope, and the Rubin Observatory. These telescopes will take new measurements and potentially improve the uncertainties on some other methods to measure the expansion rate that might agree with at least one of our existing methods. If that doesn't work, well, the theorists are gonna have their work cut out for them. As for a time frame for solving this crisis, who knows? Your guess is literally as good as mine. Moving on to our fourth unsolved question in astrophysics, and this one is more from my wheelhouse. How do galaxies form? I'm gonna be honest with you, we thought that we had this one pretty much nailed. There were still some unanswered questions, particularly on smaller scale details, but we thought that we knew generally how galaxies formed from intergalactic gas. With our existing theories of gravity, we could plug all of that into simulations that simulate the history of the universe over very large volumes, for example the illustrious TNG simulations, and get a pretty realistic galaxy population back out again. We can't get all of the fine detail with these cosmological simulations, but that's a computational limit. We can get to that with better simulations and bigger, better computers. We thought we had galaxy formation pretty much down. Unfortunately, the James Webb Space Telescope, with its ability to measure the masses of galaxies some 300 million years after the Big Bang, well, it had some other ideas. Meet Jade's GSZ14-0, a galaxy with a redshift of about 14.3, with far more mass than we thought should be possible in a galaxy so early in the universe. And it isn't the only one of them. So, these things exist. How? Now, it might be that we're okay and we don't need to completely rewrite our galaxy formation models, only tweak them. The best explanation we have so far is that stars are different in the early universe, and that means we've measured the masses of these galaxies incorrectly. This is possible. We know that more massive stars give out more light per amount of mass than stars like the Sun. So if these early universe galaxies have more massive stars, something called a top-heavy initial mass function, we'd get more light from them than from a closer, more familiar galaxy with the same mass. This would mean that we'd measured the masses wrong and got a value that was too high. But it might not be that, in which case theorists, people like me, have some work cut out for us. Another question that's arisen from these galaxies in the early universe is that they have supermassive black holes, and we don't know how they got there. Truth be told, this is actually a very much unanswered question entirely. How do supermassive black holes even form? First, let's just remember what a black hole actually is. It is not a hole. It's a really misleading name. A black hole isn't the absence of anything, really. It's the presence of so much everything that gravity is so strong that light can't escape. A supermassive black hole is a black hole with millions of times the mass of the Sun compressed down into a volume smaller than the orbit of Mercury. There is a lot of stuff there. We're pretty sure that there are supermassive black holes at the centre of almost every galaxy, and we've even taken a few pictures of some of them. Well, they're shadows and stuff that's around them. But we still don't know where they come from. The best idea so far is that they start off as a smaller black hole, perhaps the remnant of a large O-type star, which then gathers up a load of material around them, gas and dust, accreting mass, until they reach the gargantuan masses that we measure today. However, in what's becoming a bit of a recurring theme, JWST had other ideas. It found quasars, accreting supermassive black holes in the early universe, and they are too massive to have formed from accreting stellar mass black holes. But they are there. They had to come from somewhere. So, what are the hypotheses? Much like the early galaxies problem, the best bet appears to be that early universe stars were different. In particular here, the potential existence of supermassive population 3 stars. Now, population 3 stars are the hypothetical first stars that formed in the universe. They would have formed when the universe was a lot hotter than it is today, and when there were fewer elements heavier than helium, both of which would have let these stars be much more massive than stars today. If these objects did exist, after burning through all of their fuel, their supernovae could have left behind more massive black holes than stars today, massive enough to accrete mass and become supermassive, fast enough to explain these JWST observations. But this is all conjecture. We have no idea if this is what happened. We're of course trying to figure this out, but right now population 3 stars are entirely hypothetical. Despite being huge, they would still be about 100 times too faint for JWST to detect. Even looking for the supernovae, which would be brighter, it's unlikely to yield results because they'd be so brief and so rare that the odds of finding one before it vanished from our skies are also incredibly low. Our best bet is to look for the effect of population 3 stars on the 21 centimetre line emission from the distant universe. This is a specific wavelength of light that's emitted from hydrogen. And if population 3 stars did exist as we think, they'd leave an imprint, a transition at high redshifts in the 21 centimetre line emission. This would tell us when population 3 star formation started and how fast it happened. We haven't found that yet either. So those are my top 5 unanswered questions in astronomy today. There are others I didn't have time for, including exactly how exoplanets form and what fast radio bursts are. But I thought these were the biggest ones. If you found this interesting and you want to read more about this, links to all the papers I used in researching this video are linked in the video description down below. Now, I couldn't do any of this without the wonderful support of my patrons over on Patreon, who give me a small amount of money each month to make these videos possible. On screen are the names of my £5 a month education enabler patrons. All patrons get early access to videos and, from next month, a monthly behind the scenes vlog. All of this is available at patreon.com/Thomas Rintoul. If you're looking for something else to watch, here are some videos that I prepared earlier. Make sure to do the YouTube pleasantries, and I'll see you in the next one.